Hello everybody, here I am with a video about our homework. Um, we have a new homework, our first homework for this lecture. And before I start about the details, let me give you some notes about this. You can use MATLAB, Simulink or Mathematica, whichever you feel suited. Please read the questions carefully because there are some hints or there are some things that we want you to provide us, graphics, codes, comments, etc. Now, first of all, please do not send any emails about homeworks because we will be using Google Classroom for that. I have added our lecturers and my fellow colleagues who help out during the examination. I've added them all to the Google Classroom, so if you ask a question in the Google Classroom, you will most probably get answers as quick as possible, more quicker than emails, because we will all get notifications pushed. So one of us will probably provide you with some help. So it's more efficient to use Google Classroom than mails because you send a mail, maybe you've sent it to me, maybe to our lecturers or someone else, and then I'm not aware of that question, and then it's just too much work. So Google Classroom is an efficient way for communicating about the homework, about your questions. You can upload it on Google Classroom, it doesn't matter. You can just upload them until the 25th April. So please upload a PDF file, just a single PDF file, not a RAR, zip, or M file. The reason behind that is PDF is fairly portable. So if you assemble some files into a zip file, then it's not efficient for us and not efficient for you, because we're not asking about codes, we're not asking about separate figures or pictures about your solution. You have to prepare a report, by the way, and the only thing that you will submit is your report. It should have all the necessary stuff about your solution, the material about your solution, in that one single PDF file, in that report. Okay, so if you delay, if you send it late, then you will have a 15 points of deduction. You can ask any questions on Google Classroom. As I've said before, do not send any emails. And every student has a unique question file, so I have just wiped out the numerical stuff in my template here. I will upload this template, by the way, to Google Classroom, so we can communicate on this. But the thing that you should put in your report is very important, because that will be graded, and its graphical aspects will be graded. So no MATLAB codes, because we know what the MATLAB code will look like, but we want you to prepare a report that guides us through the design process. You take the system, the controller, you find the feedback, you give numerical details about them and every step. So someone who's not aware of the solution can use that as a solution manual. So that's important. You can use whatever you want to help out in understanding the solution method you're providing, because you can use graphics, tables, whatever you want. But don't provide any MATLAB code or MATLAB files If you send any M files, most probably they will be disregarded, because we're not asking that. We're asking you to prepare a report that has all the data necessary in it, and code is not that important here, because it's not about code. You have to use MATLAB code. I think you have to, and that's basically it about this. So I'm uploading PDF files every week. You can maybe use that as a template, because it has pretty much the structure that we want to have here, except the code part, of course. But give every numerical data. For example, we will see in a minute. You will define a controller with a structure, and then you have the system, the closed loop, all the polynomials, all the poles, zeros, whatever you have. Just provide it step by step. Give some nice figures that we will touch base on in a minute, and then provide some comments about that. So that's basically it. Now, about the homework itself. Well, you have a DC motor model, a transfer function, basically. And we have this control system structure here. We have a system, and we have a controller, and a feedback, unit feedback here. Some disturbance here in the which is affecting the output. And most of your time will be spent here looking at this unit feedback. Just for task E, I guess, we will use the outer stuff here. We are the F2, the integrator, and the output. This is based on a motor model, but this control system structure gives us the vehicle motion control system, basically, where we are providing an acceleration reference, and we get to measure the acceleration, and we have some disturbance affecting that acceleration. What we're trying to do is we are trying to figure out controllers, design controllers that tolerate step changes in our reference, which means that we are looking at the step response without overshoot. Because if I'm commanding a vehicle to move with 1 meter per meter squared, if I'm providing a reference, I don't want to exceed that reference, because that's my acceleration, my ideal acceleration data. So I want to track it without any overshoot. That's basically what is told here, so that the step type changes in the acceleration reference are tracked without overshoot. So this gives us the data that zeta is equal to 1. There should be no overshoot. And as fast as possible, that's about the settling time, within reasonable limits. So what does the reasonable limits mean? Basically, reasonable limits tells us that, let's say we have a vehicle, 1 millisecond is not a good value for this. It's too fast. So if you're accelerating, you most probably will use 1-2 seconds as a settling time, something in that area. So that's the reasonable part. Or the system can tell you that it has a certain limit due to the structure of the controller and the system together in the feedback structure. So maybe the system itself, the control system itself, limits you, and most probably it will. And you have to look for it for yourself, because you will see some limits, basically, and you will have a reasonable interval here, because, as I've said before, half a second for acceleration is not bad. Maybe it's fast. It depends on your choice, and it's left to you. Just be reasonable, not something that is too fast or too slow. For example, 30 seconds of settling time for an acceleration might be a little bit much, but it depends on the vehicle. I know that, and no vehicle data is provided here. But try to stick with an interval where you think it should be. And the choices are not that many. You will see that because the system has a certain limit, and we had a laboratory session about this. We've seen that a system can be accelerated in terms of settling time to a certain degree, and hope that you will see that. Now, this is provided here. We have an open loop here, and we have a closed loop here. I didn't bother to put a feedback structure in the outer loop. I didn't want to provide you a second feedback because it would be too much work, and it's too early for that. We have a feedback loop for the acceleration. So if you provide an acceleration, you are measuring the acceleration and feeding back the data, and you're constructing this loop. And then you will have a closed loop. And then we put a controller here and an integrator, because that's the relation between acceleration and velocity. And we will look at the applied reference and then the output. So what we are actually trying to do is we are trying to control the velocity of the vehicle, but we have and we've decided to control the acceleration and then the speed for some reason. Now, our first question is design a p-type controller for F1. So focusing on the inner loop here. There's no AD, there's no integrator, no F2, just AR and A and the feedback, unit feedback connection that we're used to. Okay, design a p-type controller, and you should provide the pole zero map, the resulting pole zero map, and the step response. The step response is in terms of the reference, acceleration reference, and the acceleration output. Provide the controller and resulting closed loop transfer functions, so we can see what the results look like. We have to look at the pole zero map, the step response, the controller transfer function. Maybe you can, by the way, you can provide the controller transfer function or closed loop transfer function using the pole zero representation or the TF representation. So ZPK or TF, or both of them. That would be better, because you can double check your pole zero map. If the transfer function poles and zeros are exactly placed at their place on the pole zero map, then you didn't provide any false data. That might be helpful. And looking at the parameters, for example, in this case for KP, it is important. So if you are trying to solve A, what I suggest is you might use both the methods that we've covered in our laboratory sessions. You know, there are two different methods to choose a p-type controller. One of them is graphical based and one of them is algebraic based. So use both of them, because each of these methods have constant pros, so that it gives you hints about the system. Looking at just the algebraic equations might leave you stuck, and looking just at the graphics generated during the design process might also leave you stuck. So you have to combine both methods so you can choose, for example, the reasonable limits for the system in terms of settling time. So I highly suggest you to use both methods that's available to you as tools here. So, and you have to provide the p-type controller as I'm doing it every week in the laboratory session. Define the p-type controller, use the system transfer function, do the connection, give the polynomial or the graphics, etc., and then give your solution step by step so I can understand what's happening and what is your methodology and what's the reason behind your choices. That's what I'm trying to, or that's what we are looking for, and that's what we are trying to grade here, because the knowledge is important, not the MATLAB code or something else. You have to be aware of what you're doing and why you're doing. So that's basically A, B, C, and D, because we're repeating this process over and over again with a p-type controller, pi-type controller, PID-type controller, and it seems like all these controllers, all these three structures, have some issues, some pros or cons, and then what we are asking you to do is we are asking you to choose a controller structure based on these three controller structures based on these designs that you've carried out. So based on that knowledge in ABC, you should provide a controller. So the important part here is that you will use, based on the previous designs, the knowledge. So it might look like them, but it might combine the pros of these controller structures, or it might do a slight modification that helps out if it's necessary, and it's most probably is necessary, because if there's A, B, C and they are failing, then it seems like D should solve this problem. Okay, so provide, and at this point it will be a copy paste. In terms of a report, it will be a copying and pasting task here, because they share the design methods, the methodology. So once you've written down A, once you've reported that, you will most probably copy that and modify it so that it is B and the PI controller and then PID. The only thing that changes is the numerical data, of course, some additional steps maybe, and then the comments, but we will come to that in a moment. So A, B, C, D is concerned with this inner loop without AD, without the integrator and F2, and you're giving a unit step in terms of acceleration reference, and you're looking at the output acceleration. And what you're trying to figure out is what the P-type controller does, what the PI-type, PID-type controller does, what the pole zero map looks like, the step response looks like, and what the transfer functions look like. And then you decide on a modification on the controller, and then you carry out the job. You repeat it again, and you look at the results here. Once you're done with this, in E, which is the last part of our homework, you will use two inputs here, VREF and AD, and these are concerning the output outer loop here. You're giving a speed reference, and then you're looking at the speed, but you have some disturbance in acceleration, and you will plug in every controller that you've designed in this homework. So A, B, C, D, which makes 4 different controllers here. Plug in the controller and provide the inputs here, and then look for the output. And you will have to plot them on top of each other. So if you think about it, you should use some colors for every controller and maybe be consistent in the report. Depends on you, but you have to plot them on top of each other so you can see the difference and examine them, because you will have to comment on the reasons of each of the controller's behavior. So if you struggle with applying 2 inputs simultaneously, you have 2 methods that come to my mind. One of them is using Simulink, which I didn't here. I have generated this using MATLAB, but I didn't use Simulink. But you can feel free to use Simulink. Or you can use LSIM, which is linear simulation, the abbreviation of that, which is a MATLAB code very similar to step function that we use in the laboratory. And if you point that out in the laboratory session, I might give you a quick demo. You can use you have to provide a transfer function that has 2 inputs, so a meso system, which you can do, by the way, by putting transfer functions in an array using comma separator, a multiple input single output system, because this is one of them. This is a system that has multiple inputs, VR and AD, and you have just one output V. So you have to provide that as an argument, which is a TF object, and then you give a columnized separated input signal array. So AD and VREF should be given in column. So in this case, it is a, let's say, n by 2 array, and then you give the time, which is also n by 1, and you get the result. So you can use LSIM, which I suggest, but you can also use Simulink if you're not aware, and if you do not feel comfortable about that. The only thing that's important here is that you have to generate a single plot which shows in different colors all the speeds generated using every controller designed in this homework previously on top of each other so we can compare them and comment on the reasons of the behaviors of each controller. So during the grading, you should keep in mind that the pole zero map will be looked after, the step response, the transfer functions, all the data, and all the step-by-step explanations, and also here the comments. So sometimes it happens that some students do not provide any comment. So this means that not providing a comment, which makes sense, by the way, which should be the right answer, naturally, or it could be the best of your knowledge, by the way. We will take that into account. You don't have to be writing the best comment or the most valid one. But if you're onto something and we see that out of the comment, most probably that will be enough for us. But you get what I mean. So you should comment if it is asked for. So we're literally looking at the sentence here, and we're looking for pieces that are missing. And if it's provided, then we have to take that into account. If something is missing, and that's what I mean by read the questions carefully. So please keep that in mind. So the tasks are hopefully very clear. So you should carry them out one by one. So the whole aim here is to get used to these controller design methods, and I suggest you to use both of them available to you, and then maybe use some disturbance provided to the system. And by the way, we're choosing F2 in task E using open loop strategy, and you can see that because there's an open loop here. There is no closed loop here. We don't measure the speed. We are trying to apply speed reference in such a way, since we know the system structure or transfer function, we're trying to use only that knowledge and no measurement. And this is for simplification of the second process, because I can do this all day long. I can just put some feedback structures in the outer loop, and then another one, and that's not the point here, because then you can generate as many questions as you want. P, PI, PID, and then again P, PI, PID, and then just take the combination, and it makes a lot of questions. But that's not the point here. We are just carrying out this process in order to be able to compare them concerning about disturbance here. So they should have different responses, and we will look at them, hopefully. So that's it, basically. As I've mentioned before, let me remind you again that the due date is given here, and you will be provided individual, unique PDFs that correspond to you. So do not cheat, because it will be very apparent to us looking at the PDF files that you provide, because there are different numerical data, and there are also comments which are unique to each person. So please do not cheat, because what we are trying to do is not trying to give just some grades or stuff. We are trying to help you out in certain theoretical aspects here. So please do not provide any code. That's not necessary. You have to use a classical examination style in your answers, and I'm providing a PDF every week. Maybe you can go ahead and check that out and look for every step there. And that's basically what we are aiming here for. And no RAR, zip, and M files again, because it becomes too much of a confusion at some point, because someone uploads a RAR file that has all separate figure files as PNGs or JPEGs, and then a file for every question, MATLAB files, and then zips that together. And then what we are asking here for, or what we are trying to also grade, is the layout of the report. So there's no layout in the report. And so basically you can use LaTeX, you can use Word, or you can also use handwriting, by the way. But I don't suggest you to use handwriting, because first of all, the first issue is readability of your handwriting. or some confusion about your handwriting, in order to avoid that. And by the way, you have to provide some plots which you can't prepare by hand. And we are doing all this stuff using computers. Why not using just create reports using the computer? So basically, you can, but I highly recommend not to use handwriting. You can use LaTeX, Word, and the only thing that you should take into account is that it should contain all the data in just one single PDF file. At the end of the day, you should upload a PDF file. So that's basically it. I will be uploading this onto Google Classroom, so you can ask your questions using Google Classroom as a comment to this PDF, and I will also upload this video there. So basically, I have added everyone who is responsible for this lecture into Google Classroom. So that's basically it. So hope that you can just carry out the tasks that are asked here. So that concludes all. So have a nice day, and that's it basically.